In 51, a simply supported beam of length L carries a load varying uniformly from 0 at left end to maximum at right end. The maximum bending moment occurs at a distance of our simply supported beam AB subjected to a uniformly varying load of maximum intensity W per unit length, 0 at this end and maximum at this end. Okay, total length of the beam is L. So total load on the beam will be area of this triangular load diagram. So total load will be equal to half into base is L and height is W. So total load will be WL by 2, and the reaction at support A will be 1/3 of the total load, that is WL by 6, and reaction RB will be 2/3 of the load, total load, that will be WL by 3. Now let's take a section x dash at a distance small x from left end A of the beam. So at this section the load will be, by calculation, Wx by L. Okay, so shear force at this section will be reaction Ra minus this load Wx by L, but the distance will vary from 0 to x, for the section. Okay, so after calculation, V shear force at this section x dash will be WL by 6 minus Wx square by 12. This is equation number 1. Now we have to determine the maximum bending moment from the left end A. So we know shear force is equal to 0 where bending moment is maximum. Okay, so equation 1 will be equal to 0, and if we calculate, x will be equal to L by root 3. Option A is right answer. Question number 52. If a cantilever beam carries a uniformly distributed load over its entire length, then the shapes of shear force diagram and bending moment diagram respectively are. For the cantilever beam subjected to uniformly distributed load W per unit length, having total length of the beam is equal to L, the shape of the bending moment diagram will be quadratic parabola, and maximum bending moment will be at the fixed end. The value is WL square by 2, and the shape of the shear force diagram will be triangular in shape. 0 will be at the free end, and maximum, that is equal to WL, will be at the fixed end. B is right answer. Question number 53. A portion of a beam between two sections is said to be in pure bending when there is constant bending moment and zero shear force. Option A is right answer. Question number 54. The ratio of width to depth of a strongest beam that can be cut out of a cylindrical log of wood is. So assume capital D is the diameter of the cylindrical log. Okay, and from this log we have to cut a beam of size B into D. B is the width of the beam and D is the depth of the beam. So by the geometry we can write B square plus D square equal to capital D square. We know by Pythagoras formula, this hypotenuse square equal to this square, this base square plus this perpendicular square. Okay, so we can also write small d square equal to capital D square minus B square. That is equation number 1. And section modulus Z for this beam will be BD square by 6. Now in this equation of section modulus, if we put the value of D square here, Z will become small b D square minus B cube by 6. Now to get maximum strength, we have to differentiate the section modulus with respect to width of the beam and equate it to 0. And if we do that, small b width of the beam will be capital D by root 3. If we put the value of small b equal to D by capital D by root 3 in equation number 1, then we will get small d value. Small d will be equal to capital D into root over of 2 by 3. And if we make the ratio between width to depth of the beam, the ratio will be 1 by root 2. B is right answer. 55. Of the several prismatic beams of equal lengths, the strongest in flexure is the one having maximum section modulus. Option B is right answer, because the strength of the beam is directly proportional to its section modulus. Number 56. Of the two prismatic beams of same material length and flexural strength, one is circular and other is square in cross section, the ratio of weights of circular and square beam is. We know the formula, bending moment M equal to sigma into Z. Sigma is the bending stress and Z is the section modulus of the beam. For a square beam of side length A, section modulus Z will be A cube by 6. That is equation number 1. And for a circular beam of diameter small d, section modulus will be pi d cube by 32. That is equation number 2. Since material and flexural strength same for them, equation 1 will be equation number 2, because the section modulus will be equal to each other. And if we do that, the side length of square beam A will be equal to 0.838 small d. And as both the beam made of same materials and of same length, the area will be equal to the weight of the beam for both the beam. Now if we make the ratio between weight of the circular cross sectional beam, divided by weight of the square sectional beam, which will be equal to the area of the circular beam divided by area of the square beam, equal to pi d square by 4 divided by a square. And we know the value of A equal to 0.838 d as we get earlier. Then the ratio will become 1.118. Option A is right answer. Question number 57. A flexed beam consists of a wooden joist 150 mm wide and 300 mm deep, strengthened by steel plates of 10 mm thick and 300 mm deep, one on either side of the joist. If the modulus of elasticity of steel is 20 times that of wood, then the width of the equivalent wooden section will be. We also know the formula of modular ratio is equal to ES by EW. ES is the modulus of elasticity of steel and EW is the modulus of elasticity of wood. And M is equal to 20 given in the question. Okay, so equivalent wooden width will be M into total steel thickness. So M is equal to 20 and total steel thickness will be 10 plus 10 equal to 20. So equivalent wooden width will be 400 mm. So total width will be 400 into plus the width of the wooden joist, that is equal to 150 mm, equal to 550 mm. Equation D is right answer. Number 58. Maximum shear stress in a circular cross section is 4 by 3 QAV. Option B is right answer. QAV is the average shear stress, and the maximum shear stress will be at the center of the circular cross section. Question number 59. A beam of rectangular cross section is 100 mm wide and 200 mm deep. If the section is subjected to a shear force of 220 kN, then the maximum shear stress in the section is. Width of the beam 100 mm, depth of the beam 200 mm, and the beam is subjected to a shear force of 20 into 10 to the power 3 Newton. The formula for tau average shear stress is equal to shear force value divided by cross sectional area of the beam. So we got the shear force value, that is equal to 20 into 10 to the power 3 Newton divided by cross sectional area will be 100 into 200. So and after calculation tau average will be equal to 1 Newton per millimeter square. Now to get maximum shear stress value, we have to multiply the average shear stress value with 1.5, and after calculation tau max will be equal to 1.5 Newton per millimeter square. D is right answer. Question number 60. If the maximum flexural stress in timber joist of the flexed beam shown in the figure 10.3 is 7 Newton per millimeter square, then the maximum stress reached in steel is. We know the formula for modular ratio. M is equal to ES by ET. ES is the modulus of elasticity of steel and ET is the modulus of elasticity of timber. And we also know that from Hooke's law, E equal to sigma into epsilon. Epsilon is the strain of the material and E is the Young modulus of the material and sigma is the stress of the material. So from that relation we can say E modulus of elasticity of the material is proportional to stress of the material. Okay, so we can also write M is equal to sigma S by sigma T. Now we got M, the value of M, that is equal to 10, and the value of sigma T, that is equal to 7. Now if we put these two value and calculate, sigma S will be equal to sigma T into M, 7 into 10 equal to 70 Newton per millimeter square. Option B is right answer. Question number 61. A beam of square cross section with side 100 mm is placed with one diagonal vertical. If the shear force acting on the section is 10 kN, then the maximum shear stress is. The beam is subjected to a shear force of 10 into 10 to the power 3 Newton, and cross sectional area of the square beam will be 100 into 100 equal to 10 to the power 4 millimeter square, as it is a square cross sectional beam. and tau average, shear stress average, will be equal to shear force divided by cross sectional area of the beam. So 10 into 10 to the power 3 divided by 10 to the power 4 equal to 1 Newton per millimeter square. And to get maximum shear stress tau max, we have to multiply this average shear stress into 9 by 8, and after calculation tau max will be equal to 9 by 8 into tau average equal to 1 Newton per millimeter square. So 9 by 8 into 1 equal to 1.125 Newton per millimeter square. Option B is right answer. Question number 62. A piezometric bar when subjected to pure bending assumes the shape of a arc. A piezometric beam having a constant cross-section throughout its length subjected to pure bending bends into the shape of an arc of a circle. This is because under pure bending, bending moment and the radius of curvature remains constant. D is right answer. Number 63. A beam of triangular cross-section is placed with its base horizontal. The maximum shear stress intensity in the section will be. Option C is right answer. Question number 64. A beam of I section 600 mm deep and 200 mm wide has flanges 25 mm thick and wave 20 mm thick. If the shear stress in the wave at the junction of flange and wave is Q, then the shear stress in the flange at the junction is the beam of I section of depth of total depth 600 mm, thickness of the waves 20 mm, and width of the flange is 200 mm and thickness of the flange is 25 mm. We know the formula for shear stress on beam is equal to VA y bar divided by I into B. V is the shear force on the beam, I is equal to moment of inertia, and small v is the width of the section, and A y bar is equal to first moment of area. From this equation we can write tau is inversely proportional to width of the, so we can write tau f divided by q equal to tw by capital B. Tau f is the shear stress in the flange and q is the shear stress in the wave, and capital B is the width of the, capital B is the width of the flange, and tw is the width of the wave. And after calculation putting all the value, tau f will be equal to 0.1 q. Option D is right answer. Question number 65. A beam of uniform strength has at every cross section same bending stress. Option B is right answer. A beam of uniform strength is a beam in which the maximum bending stress remains constant at every cross section throughout its length. Question number 66. The shear center in the channel section shown in the figure 10.4 will be at. Shear center is defined as the point through which the total load must be applied to produce zero twisting moment on the section. If the load passes through the shear center, then there will be no twisting, but there will be bending stress. For a channel section as given in the figure, the shear center lies outside the section on the side of wave symmetry axis. Whenever a transverse load passes through the shear center, the channel beam bends without twisting, but if the load does not pass through the shear center, the section experiences both bending and torsion. So from this theory we can say the shear center in the channel section shown will be at B. Option B is right answer. Number 67. For no tension, the plane of bending should pass through the shear center of the section. Option B is right answer. Number 68. Two beams, one of circular cross section and other of square cross section, have equal areas of cross section if subjected to bending. Two beams, one is in square section and another is in circular section. So let's say side of the square section is equal to A diameter and diameter of the circular section is equal to D. Since the areas are equal, area of the square beam A square will be equal to area of the circular beam pi d square by 4. From this we can write small d is equal to 2a divided by root over pi. This is equation number 1. Section modulus ZS for square sectional beam will be a cube by 6, which is equal to 0.167 a cube, and section modulus for circular cross sectional beam ZC will be equal to pi d cube by 32. And in this equation, if we put small d equal to 2a by root over pi, then we will get ZC equal to 0.141 a cube. So ZS greater than ZC. So for the same cross sectional area, a square cross section has a higher section modulus than a circular cross section. Hence it offers greater bending strength and more economical. You can say square beam is more economical. Option B is right answer. Number 69. If the portion which should be removed from top and bottom of a circular cross section of diameter D in order to obtain maximum section modulus is, we know the formula for section modulus. Z is equal to I by Y. I is the moment of inertia and Y is equal to distance of extreme fiber from the neutral axis. Now for a circular section, if small portions are removed from the top and bottom, then statement 1, the Y value decreases, which will tend to increase the section modulus Z. And statement 2, I value decreases also, which will tend to decrease the section modulus Z value. Therefore, there is an optimum amount of material to be removed for which the section modulus becomes maximum is differentiation of section modulus with respect to the thickness T, which will be removed, is equal to 0. And if we calculate, small t will be equal to 0.011 d. Option C is right answer. Number 70. A beam of overall length L rests on two simple supports with equal overhangs on both sides. Two equal loads act at the free ends. If the deflection at the center of the beam is same as at the either end, then the length of the either overhang is. So this is a simply supported beam AB with two overhangs CA and BD of same length small a, and total length of the beam is small l. So the portion AB will be equal to L minus 2a. Let's say capital L is equal to L minus 2a. Due to symmetry of the beam with the loads, reaction RA will be equal to reaction RB, which will be equal to 2P by 2 equal to P. And for this beam, deflection at the center will be equal to P by 24 EI into capital LQ minus 24 A square into capital L. This is equation number 1. And deflection at the free end will be equal to PAQ by 3 EI. This is equation number 2. As per question, both deflection are equal to each other. So equation 1 will be equal to equation number 2. And if we do that, after putting capital L equal to L minus 2a in this equation, small a will be equal to 0.152 L. Option A is right answer. Question number 71. A beam ABC rests on simply supports at A and B with BC as an overhang. D is center of span AB. If in the first case a concentrated load P acts at C, while in the second case load P acts at D, then the deflection. For case 1, the simply supported beam AB with overhang BC portion subjected to a load P at the free end. This is case number 1. We have to determine the deflection at point D. And in second case, the same beam is subjected to a load at the point D, but we have to find out the deflection at point C. As per Maxwell's reciprocal theorem, we know del DC equal to del CD. That means deflection at point D due to point load at point C is equal to the deflection at point C due to the point load at point D. Hence, deflection at D in case 1 is equal to the deflection at C in the second case. A is right answer. Number 72. The slope at the end of a simply supported beam of span L with uniformly distributed load W per unit length over the entire span is given by. Option C is right answer, where EI is the flexural rigidity of the beam. Here the simply supported beam subject of total length L subjected to a uniformly distributed load W per unit length. The slope at the both end A and B will be equal to WL by 24 EI, and deflection at the center of the beam will be 5W L to the power 4 by 384 into EI. Question number 73. If the deflection at the free end of a uniformly loaded cantilever beam is 15 mm and the slope of the deflection curve at the free end is 0.02 radian, then the length of the beam is. Here the cantilever beam AB subjected to a uniformly distributed load of W per unit length of total length of the beam is equal to L. The slope at the end B will be equal to WL by 6 EI, and deflection at B will be equal to WL to the power 4 by 8 EI. Now if we make the ratio del deflection at B divided by slope at B, which will equal, which will be equal to 3L by 4, and L will be equal to 4y by 3 theta, and we have got the value of y and value of theta, and if we put the value, L will be equal to 1 meter. Option B is right answer. Question number 74. A simply supported beam ABC of length L carries a concentrated load P at an intermediate point B. If the slope at A is 0.75 times the slope at C, then the length of the portion AB is equal to. This is our simply supported beam AC. Let's take a point B at a distance small a from the end A, and at this point B, a point load is acting, that is equal to P, and the load and the length BC is equal to small b, let's say, and total length of the beam is equal to L. So slope at end A will be PAB into A plus 2B by 6 EI L. This is equation number 1, and slope at C under this load will be equal to PAB into 2A plus B divided by 6 EI into L. This is equation number 2. And in question given theta A is equal to 0.75 theta into C, we can also write theta A is equal to 3/4 theta C, and if we put the value of theta A and theta C in this equation, we will get A plus 2B is equal to 3/4 into 2A plus B, and A is equal to 5/2 into B. We also know A plus B is equal to L, total length of the beam, and the value of A is equal to 5/2 into B, and if we calculate B will be equal to 2L by 7. As A plus B is equal to total length of the beam is equal to L, so A will be equal to L minus 2L by 7 is equal to 5L by 7. C is right answer. Number 75. If the deflection at the free end of a uniformly loaded cantilever beam of length 1 meter is equal to 7.5 mm, then the slope at the free end is. The cantilever beam of total length equal to L subjected to uniformly distributed load W per unit length. Deflection at end B will be equal to WL to the power 4 by 8 EI, and slope at the end B will be equal to WL cube by 6 EI, and deflection at B divided by deflection slope at B will be equal to 3L by 4, and we have got del B equal to 7.5 mm equal to 0.0075 meter, length L equal to 1 meter. After putting all the value in this equation, we will get theta B is equal to 4 into 0.0075 divided by 3 into 1, which will be equal to 0.01 radian. Option A is right answer.